Hi, this is a recording of the final exam questions or the answers to those questions. So what you see here is your final exam, and here's the first question. So the first question I thought was kind of straightforward. So instead of so what I'll do is I'm going to use a text editor. Let me bring it here so that we can look at both the C code on this side and also the assembly code on this side by side. So one thing you can assume, you don't need this, but you can assume that these definitions are used to define the three variables. So y goes here, okay. So we'll put it at the bottom because I intend to actually run this code at some point. Alright, so the first thing we need to do is to implement if w is less than or equal to x plus y. Okay, and it has an else corresponding to it. So anytime we have a conditional statement and it has an else portion, it means that we also need to identify the end of the else. So we have end if here, and the end of the then branch has to jump around it. So LDIA and if JMPA, so that one is needs to be there anyway. Alright, so right here we need to compare w with the sum of x and y. So we need to do this first. There we go. So now we have the value of x in register A, and then we'll go ahead and do this. So now we have the value of y in register B, and we can add these two. So we'll add B to A. So now B is free again because we don't need the value of B anymore. Then we can do LDI B with W and do LD B indirect B. And at this point, B has the value of W. So if I just kind of comment here, I would say A is x at this point, and over here A is y, or B is y, and at this point we have register A being the sum of x and y. And note how I'm not changing the values of the variable either. And then at this point we have B equals to W, so all that is left to do is to do the compare. The order of the compare is important. If I do it like this, CMP W, BA, this will be comparing W to x plus y, and whatever the relationship is ending up here is whatever I'm using to do the branch. Now you can do it this way, it works. It's just that it's not the easiest way to do it. But let's go ahead and do it this way because it's preserving the order of the comparison up there. So what we need to do here is to remind ourselves, when do we go to the else label? Okay, and the else label is going to be here. Alright, so we basically want to say if w is greater than x plus y, we want to go to the else label. But there's no direct flag that we can use to do this. And the only flags that we can use are JL. Now remember, in here it is specifically just int 8 underscore t and not u int 8 underscore t, so the numbers are actually signed. If they're signed, you have to use the JL instruction instead of the JC instruction. So we have to do the opposite of, let's go there, because we have to now define a continuation point. Okay, we'll call the continuation point then, which seems to make sense. So basically we say JL, okay, LDI, we can reuse any one of these registers, so we'll reuse A for then, okay, and then we say JL to then, because if W is less than x plus y, we want to go to the then branch. That's one reason to go. But then we also have to say JZ to then. Okay, I keep making this mistake because that's the I386 instruction set. But okay, now I fixed it. So JLA and JZA they're both needed because this means if less than or equal, go to the then label. If we end up here, which means we did not take the L branch or did not take the Z branch, then we have to load LDIA with the else branch, because this is the time that we want to go to the else branch. So we say JMPA because it's unconditional. Alright, so now we just have to figure out what to do when we get to the then branch. So when we get to the then branch, we just want to subtract the value of y from the value of w. So we'll do LDIA with the label y, LDA indirect a. So at this point, a is the value of y, and then with LDIB with w, LDB indirect b. So now b is the value of w. We'll do the subtraction. We are subtracting a from b, so that b is now w minus y, and then we have to store that back to the variable w. And since I chose the wrong, I didn't choose the most optimal register here. If I put it into register C, then I can keep using register C here for the store instruction. So we store where C points to, which is W, the result that is stored in B. So now we say W is W minus Y because W is getting the value of B. And that concludes the then branch, and then we have this unconditional branch to around the else branch here. Now, if you put a halt instruction here like this, I would give you full credit, but it is better off to branch to the end because there's no telling how much code is after this. Okay, and the else branch is easier. We just want to put a 0 into W. So there are several ways to do it. You can do LDIA with W, and then do a LDIB with 0, and then do a STAB that will store the 0 to the W. Okay, so W equals 0 is here, and over here we can just put a halt instruction to basically say, okay, let's stop doing it here. So we can test this code by initializing WXYZ in different ways. So let's go ahead and test this code, okay? Because I hate to give you a solution that does not work. So copy and go to my assembler and do a paste here. There we go. Check for error messages. No errors, and I'm going to delete the rest of this spreadsheet, which is not needed. Okay, so I'll delete this. So now we have the actual code, and to test this code, let's go back to the original code here. So we want to be able to check in both cases whether W is less than XYZ or not. And they're all zeros the way they're initialized, which means, well, that it's not going to be very exciting, because if you subtract 0 from 0, you still get 0. If you add 0 to 0, you still get 0. So the code doesn't really show you any actual result. So we want to make W, and we also want to check whether the signed comparison part works or not. So we want to use, say, negative values. Okay, so let's say we want W to be -1. And we want x plus y to be 2. Okay, so x is 1, y is 1, w is -1. So let's go back here and change w to -1, which is the same bit pattern as 255. And we want to make x 1. Let's make y 2. Okay, just so that they're different, like so. And we go to the RAM file. Everything's good, so we'll go ahead and download the CSV file into my temp folder, and we'll save it as let's see here, Q1. Okay, Q1.ram, and then we switch to the emulator, reset everything, and reload the RAM program. This is Q1.ram. Alright, so we got everything here, and we'll just go for full speed simulation. It has ended, so we want to check the values of w, x, y, and we want to be able to predict what the value is supposed to be first. Okay, so we'll want to switch back to the browser, and no, not the browser. We want to switch back here. So the way we did it was w has a value of -1. So let's see. Let's go back to the question itself. It's easier to read here. So w has a value of -1, and x has a value of 1. Y has a value of 2. And -1 is less than or equal to 1 plus 2, which means we should get here. And so we are subtracting 2 from -1, and w should end up with a value of -3. -3 is represented by 253, or the same bit pattern as 253. So now let's switch back to the emulator. Oh, wait, one more thing to do. We have to find out where w is. So we have to go back to the assembler page and find out where w is defined. W is at location 35. Okay, so nope, that's not true. This is not the this is the definition part. So we want to look for the definition of w, and w is here. It is at location 35. Oh, okay, that's right. That's actually the reference of w. It resolved to 35, which is correct. So w is at location 35. Switch back to the emulator. Go to the RAM. And 35 is 23 in hexadecimal. So 23 is this location here. So FD is correct because FF is -1, FE is -2, FD is -3. So the code does work correctly with that branch. But this is too early to celebrate because we don't know whether it's going to work in the other case. So let's get rid of this window because it doesn't apply to what we are doing here. Okay, there we go. Oh, that one doesn't really apply either. So let's go ahead and get rid of that. Here, there we go. Okay. So we want to check with the other branch where w is greater than x plus y. Okay, so we want to make the sum x plus y to be less than w in this case. And we can just tweak this code here, or we can just reload. It's better to reload it first because I want to reset the entire state of the processor, and then go ahead and load the same program in, and then we'll go ahead and just hand edit a few things. So this is -1, and we want the other one to be less than this, so we can easily do that with a FD over here and a FC over here. So we have a -3 and a -4. -1 is greater than -3 plus -4. So in this case, we should see this location being zeroed out because that's what the else branch is supposed to do. Let me show you the code corresponding to that. Go back to the browser, go back to the question itself. So w is supposed to get a 0 when w is already greater than x plus y. Okay, so let's go ahead and simulate its code. Okay, close this window. Go back here, go for full speed simulation, turn it off, and we can see that we can already see the location to 0, 0. It does work correctly, but I'll just double check. This is x, this is y, and this is w. W is indeed zeroed out, so the code does work. Your code doesn't have to be exactly the same as mine. It doesn't really have to be the same because obviously we can choose different registers. You can optimize the use of registers a little bit better so that you can store the address of a label and reuse it a few times. But as I just need to check the logic of your code to make sure. This is one of the more important part is how you do the branching, and how you do the compare. Whether you know how to get to the value of a variable is important. How you identify the end of the then branch and make sure it doesn't slide into the else branch, it's important. And as I said, if you use a halt instruction here to stop the then branch, it's okay. It's not the best, but it does indicate that that's the end of the then branch and not slide into the else branch. So those are the things that I'll be looking for in that particular question. Okay. Alright, so let's move on to the next question. The next question is question number 2, which is a disassembly type of issue, a type of problem. So what I'll do is I'm going to copy and paste this code. So copy and paste it into a new tab of the editor. Okay, so we can keep the other one around. Alright, so here we go. So now we have a paste here. So as I have indicated before, the first thing I do is to look for the branching, the jumps, okay, because the jumps are indicative of many items or many things. This may not be the best way to present it. Okay, I'm gonna switch to a spreadsheet for presentation purposes. So let me switch to the shared folder so you can see it. Okay, there we go. And I'll make a folder, and we'll call it final exam answers. There we go. Okay, so we can go ahead and create a Google Sheet over here. The best part of using Google Sheets for this purpose, which is the answer of question number 2. Okay, I thought I'd do a Control-V to paste. There we go. So the best thing about doing it this way is I can merge cells so that I can combine several cells and indicate, okay, together these cells are doing this particular thing. As I said, I start with a jump instruction, and here's one jump instruction. When you see a jump instruction and it has some label reference and a label definition like that is kind of sandwiched in between, and we're doing something with a stack like this, and over here there's a pretty good chance that this is a call, but we have to double check. So when we double check, we look at these two instructions together. Oops, I want to merge these two cells. No, that's not what I want. Okay, let's try that one more time. Merge. Okay, the shortcut keys don't work in Google Sheets, unfortunately. So this is for decrementing, decrement D. And then these two instructions together is storing the return address, main return address, onto the stack, where the stack pointer is pointing to, where we just allocated a single byte. So we say merge all. We say store return address. And when you look at these two, it's the actual jump or continuation of execution in the subroutine. So this is jump to supp6, okay, which is the actual call. So when we look at all of these things, then we can say all of these items together is really just calling supp. Now at this point we don't know whether it has parameters or not, so we'll just say, okay, this is a call to supp6, and then we'll say this is the end of main, okay, return 0 and a close curly brace, and this is the beginning of main, and we'll just do it like that. Okay, curly brace, like so. There we go. Okay, so we have something here, and then we have this kind of obscure thing that we are loading A with X, and then X is later on defined here to be the label of the first of these 4 bytes. Okay, so we normally wouldn't do anything like that unless it is a parameter. So it seems like we're passing the address of X in this case. So we'll go ahead and add that part here. Okay, we'll say that we are using the address of X as a parameter. Okay, now we get to the subroutine and see if we can pick out things. We kind of note that at the end of a subroutine it has to do the return, and once again we start with a jump instruction, and then the register it uses for the jump is B, which is retrieved from where the stack pointer points to, and then we have these two instructions to add one to the stack pointer. So together these 4 instructions are really just saying return. Okay, so we'll merge these cells. and say that this is just basically doing what the return is doing. But we also notice that register A is not used in here. So that means, well, maybe we have a return value that is specified in A, but we don't know yet because, I haven't analyzed that piece of code. And then over here, we also see return address and a whole bunch of operations that has to do with the stack. Okay, we are decrementing the stack. We are allocating a byte here because C has a value of 1. We're subtracting 1 from the stack pointer. We're allocating a byte. We are storing the return address, which is defined here, onto the stack, and then we are continuing execution at sub 1. So that means we are definitely making a call here. And as a result, we combine these cells and say that there's a call here to sub 1, and it's recursive. Now we kind of know that sub 1 is using a parameter, but since we haven't really tracked down how we use register A, we don't know what we are passing yet. Alright, so when we get to the entry point of sub 1, okay, so this is sub 1, this is the prototype of sub 1, which is subject to be changed later on. Okay. We notice that we are using A right away, but remember, we cannot assume something to be in A unless it is a parameter. So we know that A is a parameter of some kind, so we put A here, and then we say that it is the address of something. Okay, we know it's the address of something because that's how we passed to parameter A here. Okay, so the first thing we do is we dereference A, so that B is the value that is pointed to by A, and then we put a 0 into C, and then we do a compare. Okay, so let's combine these three and say that we're comparing here. So merge the cells and say that we're comparing whatever A points to with 0. Okay, but we don't know the nature of the compare, so I'm going to put a question mark here to indicate that we do not know what relationship we're looking for. This is just loading the label else, and the JZ is going to the else branch. So if a JZ is going to the else branch, the branch or the condition to go to the then branch is opposite to that, which means we are looking for something that is not equal to 0. Okay, and because of the label else, we also know that we are having a conditional statement, and the else branch is starting here. So we know there's an else here, and this must be the beginning of a conditional statement. So we'll go back here and change that and say this is the condition of the conditional statement. And if whatever A points to is not 0, we want to continue with the then branch. Otherwise, we want to go to the else branch, which is here. Okay. Continuing with the then branch, okay, the then branch doesn't do a whole lot. We are loading register C with a immediate value of 1, and then we add it to A, and then we call sub 1 right away. So that means we are calling sub 1 not with the original A, but with 1 added to the A that I already have. Okay, so you can either do it this way, or you can say A gets A plus 1, and then put an A here. But the point is, when we do the recursive call, the parameter that we are passing is 1 more than what is passed to me. That part is important. Okay, and then after that, after we return, what we do is we add 1 to A. But remember, register A is used both to pass parameters and also to specify the return value. So this adding 1 to A is actually just adding 1 to the return value of A. So that means we are looking at the return value here and say, oh, whatever it is, add 1 to it. Okay. And because we're adding 1, we are storing this eventually back to A. You can represent it like this. Okay, that's perfectly okay. So, but we also have to extend the merge here so that it is all the way down here. So let's see if we can do it that way. Merge all. Yep, it does do that. Cool. Okay, so now we say this is the end of the then branch. Okay, let's figure out what it is doing with the else branch. So the else branch is just loading A with a 0. Okay, fine. Let's just specify that. All right. So now we are we kind of know what register A or how register A is being used, but in a subroutine that returns a value, the value of A is actually the return value. So we can redundantly specify a return A here. Okay. So that's basically what we are doing. So let's just kind of look at this code here and see what we are actually doing. So we are in the main subroutine. All we are doing is we are calling sub1 with the address of x. Now x is the label of one single byte, which is the first of the 4 bytes. And then that's the end of the main subroutine here. And then in the subroutine sub1, we know that we have a parameter a, and you can also specify, we kind of know what a is, because every time we are just adding 1 to it, which means the size of what it's pointing to is just 1 byte. So you have several choices here. If you want to, you can say int you unsigned int with a bits. A points to unsigned a-bit integer. You can say it is signed. You can say char. They all work. Okay, because I have not used anything to imply what is the sign of the parameter or what a points to. And then the value that is being returned is a number. It is either an int 8 or uint 8. Okay, so you can specify int 8 underscore t. You can also specify uint underscore t. Both will work because I have not indicated the use of negative values, which means it may be signed, it may not be signed. We don't know. Okay, there's not enough information to differentiate whether it is signed or not. But we know it's a number, it's not a pointer. We know that part because when we go to the else branch, it's get a flat 0. But then the recursive call is just adding 1 to whatever the next invocation is returning, which means the last invocation returns a 0, the second last will return a 1, and then the next one's going to return a 2, and so on. So we know it's returning just an integer. So we know this part, and the main part is over here, but we are not storing the value of the return value. So if you leave it like this, it's fine. There's nothing wrong with this. And about x, this is not required. Okay, if you want to, you can specify the type of x2. Now, because there are no additional labels for these bytes here, in C, it simply means that x can be. There are several ways to represent it. Okay, by the way, so if you want to look at x as a 32-bit integer, you can. Okay, it's just that when you do the call to sub1, you have to cast it as a char pointer, because that's how we are treating the pointer in sub1. Okay, but the more obvious way to do this is simply to declare x as an array of 4 bytes, and the 4 bytes are the ASCII code 48, which turns out to be, if I remember correctly, uppercase A, 49 is uppercase B, 50 is uppercase C, and a 0, which is the null terminator. Okay, so this part is optional. You don't have to declare x as an array of 4 bytes, as long as you specify that we are passing the address of x to sub1. It's good. Okay, you don't have to tell me what x really is. So there are only certain key components that I'm really looking for. One is the call to sub1 with a parameter that is the address of whatever x is. And by the way, you can take the address of an array. It's just really the address of the array. So whether you take the address of or not really doesn't matter in this case. As long as x is an array, it is automatically the address of the array. You have to be able to identify the condition of the conditional statement. If you want to do the shorthand, that's fine. Okay, the shorthand of this is not to specify compared to 0, to make it implicit. That works too. Over here, excuse me. Over here, you can either increment a and then pass, use the incremented a as a parameter, or you can not do this part and do the a plus 1 over here. Okay, either way works. And you have to remember that we are using the return value of sub1 and add 1 to it. So you can either specify this is the return value here, just do a return directly over here, or you can do it like this and say that A is storing that particular value, and then the other one is specifying a return value of 0. In other words, if you don't want to do it this way, you can always do it like this. Okay, so get rid of this and specify a return value right away here, because there's no extra code involved in this program. So this is really just return a 0, and this part here is really just return supp6 a plus 1. Okay, so that's one way to represent this program. And just checking the curly braces here, and we'll need to okay, so it does have that, it's just not shown because I have not make it wide enough like that. Okay, so that's the solution of the second question, and let's move on to the third one. The third one is to use microcode slices to implement the return instruction. This one was intended to be kind of easy because the return sequence is already here and it meets all the requirements. Register A is not involved. D is used as a stack pointer. We can only use register B and C as scratch registers. So they're all specified here. The only thing that's kind of tricky is the LDI instruction, because that's the way we load a 1 into, so that we can add 1 to the stack pointer to reclaim that 1 byte. So the RET instruction will also have to basically implicitly have a byte after the opcode to specify the constant of 1. But by itself, it is not parameterized. It has no register X and no register Y. So basically, all we need to do now is to look up the slices for these 4 instructions and just put it here. So to do that, depending on whether you have the worksheet printed, if you do, that's a pretty easy thing to do, because you just look it up and copy all of these slices. So this is the one for the LDI, and when you look at what the question is asking, we want the first one to be LD, B, and then indirect D. So we want to load indirect, which is this one here. Okay, so just copy all the slices and make sure that you use the right registers. And then the next instruction, the next slice is the LDI, and to look it up over here, the LDI instruction is it will take 2 slices to do it. It will take row 8 and also row 10 to do the LDI. So that takes up 2 slices. And the next one, clicked the wrong key. There we go. So the third slice is the add instruction. So you go to the worksheet, go to the add instruction, which I don't have, but it's really close to the subtraction instruction. It's really close to this one, except the ALUOP is different because it's going to specify an add instruction. And then the next slide is the JMP instruction, which is PC equals register something, and pretty sure I have that. There you go. So this is the last slice. Now register, you have to kind of change register A to some other register. So in this case, it is register bank output 0, if I remember correctly. That needs to be so it's register bank output 0 select. That has to be changed accordingly. But basically, we're just looking up slices of instructions that we already know and piece them together. Okay, so that's kind of question number 3. And then question number 4. Question number 4, I think this is something that we might have looked into in class. But question number 4 is just this. Okay, so LDIA So we want to implement the same thing, or something that has the same effect as this. Now remember, we only have JO and JS. We don't have the JNO and the JNS. So what you do is you LDI with sign equals to 1. Okay, so S1 represents that particular label, and they just say JS. Specify which register, right? There we go. Okay, so you have S1 here as a label, which also means that if I continue execution here, we know that sign is a 0. If sign is a 0, the way we specify JL is simply a JO, okay, LDI A with L1, because L1 is indicating where we originally want to go when the L flag is on, but except we don't have an L flag in this case. So now we have a JO to A, basically to go to the label L1, because at this point we know that the sign flag is a 0, but the overflow flag is a 1. So the exclusive OR between these two is the L flag, and that's why we want to do the branch. And if not, we want to go to a continuation point. So we say LDIA with a continuation point label, which we'll define here, because that simply means that we are not going to branch, and whatever is following the JL instruction is going to be here. Alright, so if S1, if sign is a 1, okay, so if we get here sign is a 1, we basically say LDI A with the continuation point and then the JO to A, because if the sign flag, okay, if the sign flag is 1 and the overflow flag is also a 1, the L flag is going to be 0, which means we should not go to label L1 and just continue execution after the JL instruction. So that's why we want to do a continuation here. If that does not happen, it means the overflow flag is a 0, but the sign flag is a 1, which means that the L flag would be a 1 in this case, and we should continue execution at the label L1. So we do LDIA with L1 and a unconditional branch in this case to A. Oh, we forgot one thing here, don't we? Because we forgot a JMPA in this case. Otherwise, loading a register with cont doesn't really do a single thing. So there we go. This is the solution of question number 4, and I will continue with question number 5 after a little bit. So I'm gonna upload this much to YouTube first, and continue to work on this in maybe about half an hour or so.